Then once we complete that, we will move on to the next section of our syllabus, which is friction. So friction is going to be basically like a continuation of Newton's laws of motion, but including situations where the surfaces on which blocks are moving, etc., are going to be rough. So we will have to consider the coefficient of friction and the frictional force as an additional contact force when an object is moving on a rough, or what we call a frictional surface. So we'll come to that when once we complete the problems of Newton's laws of motion. So anyway, let us begin with the questions from H.C. Verma. So first of all, if you have any doubts pending from H.C. Verma, just drop me a message with the question numbers. I will start with those questions, and then there are a few questions that I want to separately discuss. We will complete those and then finally move on to friction. So this is session number 9 in Newton's laws of motion. Yes, we will discuss about spring force also. Okay, but first of all, let me know if there are any questions which are pending from the doubts point of view from H.C. Verma. I think last time we had discussed up to question 35 or something, if I'm not mistaken. Yeah. Okay, question 41, we will come to that. Anything before 41? Have you gone through question 39, 40? 22C, okay, let's start with that. Okay, so in this type of question, okay, 22C and 26, okay, let's go through these two questions. Okay, so in 22, the first thing you have to do is you have to find the tension in the string, and once you find the tension in the string, then you can find the reaction force at the clamp of the pulley, because you will have to make the free body diagram of the pulley to understand how much that reaction force is. Okay, so of course, keeping in mind that it's a massless pulley, so the pulley's own mass is negligible or tending to zero. Okay, so this is a massless pulley, and the two masses which are attached by again a massless thread are M1 and M2. So M1 and M2 are given to us as 300 grams and 600 grams respectively. Now the C part of the question is asking us to find out the force exerted by the clamp on the pulley. Okay, the force exerted by the clamp on the pulley. Okay, so when you look at the pulley, it's like this kind of an object, but its own mass is negligible. Now this is the clamp of the pulley. It's attached to the ceiling like this. So this one here, this is the clamp. Okay, so what is happening here, you will understand, is that the tension in the strings, I mean tension in the string on both the sides, this is going to be pulling, because the string is going around the pulley like this. So from both sides, the string is going to be pulling down with tension T and tension T like this. Okay. So when you make the free body diagram of the pulley, you'll understand what this clamp force is all about. Okay. When you so you understand this pulley is being pulled down from both the sides with tension T and tension T like this. Even though it doesn't have any mass, but the string is pulling it down. So this clamp will apply some upward force like this on it. Okay, so that is the force that they are asking for. So what you have to do is you have to solve this system first of all to find out the tension in the string. Okay, and then you make the free body diagram of the pulley. So FBD of the pulley will be, like this disc of the pulley. It's experiencing two tensional forces downwards. So it will experience some kind of reaction force to the clamp. So this is the force exerted by the clamp on the pulley. And remember, the pulley is massless, so there's no weight of the pulley. So, and of course the pulley is also at rest and it is massless. So F has to be equal to 2T. Okay, so basically you have to find out tension. Now to find out tension, you have the individual free body diagrams of these two blocks. Okay, so you have M2G minus T is equal to M2A. You have T minus M1G is equal to M1A. So from this you find out how much tension is, and then you substitute that here. Okay, so if you solve these two equations, you can see that M2G minus T upon M2 is equal to T minus M1G upon M1. So we can say that G minus T by M2 is equal to T by M1 minus G. So T into 1 by M1 plus 1 by M2 is equal to 2G. So the tension is equal to 2 times M1 M2 upon M1 plus M2G. So once you got this from these equations, and of course you will substitute the values of M1 M2 to get this. You substitute this here in this equation, and you will get the force as 4 times M1 M2 divided by M1 plus M2 times G. Now you just numerically substitute M1 M2 and G, you will get that force. Okay, so hope this question is clear. This is question 22 part C. Okay, and so this is clear. So just note down this, those of you who haven't. Then we'll do question 23 next, and then 26. Then we'll come to the remaining questions. So question 23, question 26, then 31, 33, 39, 37 also. Yeah, the chapter is almost over. We have to just discuss about spring force. Conceptually, there's only one thing left. Actually, a couple of things: spring force and something called wedge constraint. Okay, wedge constraints and spring force. Okay, but first we will complete these problems from H.C. Verma because they don't involve these additional concepts. Yes, in major test 4, all this will be coming. Spring force is very easy. It will just take 5-10 minutes to understand. So the main thing is for major test 4, the main part of Newton's laws of motion is pulley systems, constraint relations, pseudo force, all these things. Newton's laws of motion. So start solving na, the module. If you haven't started solving the module yet, start solving. You only have to solve na, I don't have to solve the module. After we finish HC Verma, we will keep some time for discussing the doubts from the module also. But entire Newton's laws of motion, Ansh, we have completed Newton's laws of motion. There's nothing else in it. Friction is a separate chapter. Next chapter we'll be discussing is friction. I told you. HC Verma Newton's laws of motion chapter is the entire chapter only, na beta. We have completed that. We are just discussing the last few questions. Just make sure that you have completed HC Verma level questions. That will be enough for the test. Yes, pseudo force and non-inertial frame is part of Newton's laws, beta. It's part of the questions we solved in HC Verma, na? All the types of questions that you require for Newton's laws of motion that are there in HC Verma. So once you complete the HC Verma exercise, you should be prepared for the test. The module exercise is for extra practice for you. Okay, but all the concepts that you require are there in HC Verma. That is why we are using the HC Verma as the first point of reference. Okay, anyhow, let's come to question 23 next. Okay. So the same thing now, what is happening? You're stopping the mass M2 for a moment after t equal to 2 seconds. Okay. So let's understand this question in detail. So in question 23, you have that same system that we had in 22. Okay, but you're just stopping this mass. So t equal to 0, they both start from rest. Okay, but immediately they have an acceleration like this. Now that acceleration also we had seen from the equations. We had previously, we just saw these equations. So when you solve the acceleration from this, you will get this relation. This all you've done in question 22. So the acceleration will come out to be g by 3, okay, according to the masses which are given. Now in this question it's saying that at t equal to 2 seconds, okay, the mass m2 is stopped for a moment. Okay, for just a moment it is stopped, or just an instant it is stopped and released. So after how much time the thread will become tight again. Okay. So let's understand this. Okay. So see what is happening is that if you compare this time with a time 2 seconds later, this block would have come down a little, this block would have gone up a little. So at t equal to 2 seconds, just before you hold this one, this is having an upward velocity, this is having a downward velocity. The string is still having tension because you haven't stopped the other block. So this is still having that same acceleration E. Okay, so at t equal to 2 seconds, just before the block M2 is stopped. Okay, this is the situation. Just a moment, yes. Yeah, so just before you stop this block, okay, what is happening is that the velocity will be equal to at. So it will be 2g by 3. Okay, or you can write it as 20 by 3 meters per second for each of them. Okay. Now what happens? You stop this block for a moment. So just after M2 is stopped for a moment and released. Now at that point, what will happen? Because you stop this block, the string becomes loose. So the tension disappears. And because you stopped M2, what does M2's velocity become? It's become 0. The velocity has become 0 and the string has become loose actually. On both sides, the string will become loose. So the tension disappears, but you did not stop M1. So M1 still has that velocity like this of, so M1 has a velocity of v equal to 2g by 3 upwards. Okay, but because the tension has become 0, it's now having an acceleration of g downwards. Okay, and what about the state of M2? M2's velocity has become 0 because you stopped it. Okay, and because tension in the string becomes 0, it also has a downward acceleration of g. So its acceleration is g downwards. This is the state for M2, this is the state for M1. In the moment just after we have stopped this and released. Okay, just after M2 is stopped and released, this is what is happening. Okay, the string has become loose. So tension has become 0. So because tension has become 0, that is why both of them are now having a free fall acceleration of g. Okay, so now if I see after some time, after delta t time from here, okay, from here onwards after another delta t time, what will happen is that this block would have fallen from this by a displacement of S2, and this block would have gone up from here, from where the string had just become loose, by let's say S1. Okay, and at the moment when the string becomes tight, S1 should be equal to S2. So if at this time delta t the string is becoming tight again, you can see geometrically the condition for the string to become tight is that this should have come down by the same distance as this has gone up. So it's going back to this state just before. Okay, so if at this point of time the thread just tightens again. Okay, so once again the thread has just about become tight. So the condition for the thread to become tight again is that S1 should be equal to magnitude S2. Now S1's magnitude will be what you are getting from the initial condition of M1. See what is happening to M1, it started with an upward velocity of v with a downward acceleration of g. So S1 in time delta t will be how much? It will be v delta t minus half g delta t square. And S2 is the displacement of the second block. So the second block is in free fall starting from rest. So its downward displacement is half g into time square. So from this you will get the time that v delta t should become g delta t square. So either delta t should be 0, which is not the case, that is the initial condition, or delta t should be v by g. Now this is the case. And what is the value of v? It is 2g by 3. So this time should become 2 by 3 seconds or 0.67 seconds. So 0.67 seconds after you have stopped that block M2 and let it go, that is when the string is becoming tight again. That is the solution to this question. Okay, so actually the final part of the solution is all about kinematics. Now, the only part of Newton's laws was the part which is common to 22, which is finding the acceleration. Now once you found the acceleration using the free body diagram equations, this is g by 3, the rest is just kinematics. You're using the relation that v is equal to u plus at. Okay. Then for example, here you are using the relation S is equal to UT plus half AT square, that kind of thing. So just go through the solution once and make sure the concept is clear. Then we'll discuss the next question. Okay, so hope this question is clear. Now let's move on to 26th question next. Now 26th is a comparatively easy question. I think most of you will be able to get it yourself if you just pay attention to the free body diagram. Okay. So in 26, okay. So we have this smooth horizontal surface with a pulley attached at the end like this. So one block attached here, one block attached here. Okay. This surface is smooth. Now these blocks are mass M1 and M2. Okay. And we are applying a force. An external force is applied to this block. Now that force's magnitude is given to us as M2 by 2. So magnitude of that force is equal to M2 by 2G. Okay, so half the weight of this block. So we have to find the accelerations. Table is smooth, find the acceleration of M1 and M2. Okay, so you see that because this force is less than the weight of this block, this system will tend to accelerate like this, in spite of you applying the force like this, because the weight is more than F. So the pulling force downwards will dominate over the pulling force towards the left. So ultimately this is what will happen. So on this block, the forces are like this. On this block, you don't have to worry about the weight because normal reaction will balance that. Okay. So for M1, we have the equation T minus F is equal to M1T. Okay, and don't worry about the weight, it is balanced by normal reaction. For M2, however, the weight is pulling it down. So weight minus tension is mass into acceleration. Now to solve for acceleration, just add the two equations, very simple. So tension cancels out. So M2G minus F is equal to, on the other side, M1 plus M2E. Now substitute this value of F that was given to us. This was given. So substitute this over here. So M2G minus M2G by 2 is equal to M1 plus M2E. So as I said, it's very simple, trivial type of question. E will become M2 upon 2 times M1 plus M2 times G. This should be your answer. Okay, so take this down quickly and then we'll move on to question whatever. I think 31 was the next question we are targeting. Yeah, question 31 we'll discuss next. Okay, let's move on to question number 31 next. Okay, now in 31 we have this kind of a situation now. This pulley here is connected by a clamp, and the thread that is going around this pulley is then actually need to go around another pulley over here, and the end of the thread coming out from this pulley is now attached at the clamp over here, whereas this pulley is of course attached to this block which can slide on this surface like this. Okay, so as usual, frictionless surface. Now this particular block has a mass of 2m, whereas this end of the thread now is attached to a block of mass m. So you can see that there will be some uniform tension acting like this through the thread. Now you can also see that there's a constraint situation here. What is happening is that if this block moves by a certain distance, okay, so if this block moves by a certain distance x over here, it will release how much thread? It will release 2x amount of thread. So this block will end up coming down by 2x. Okay. So basically what we can see here, the constraint wise, is that if A displaces horizontally by SA is equal to x, okay, so this is the displacement of A, then this one will have a downward displacement of 2x. So what happens when this displaces by x? It will release 2x thread length. Okay. So as a result of that, the block B will displace downwards, okay, by SB equal to 2x, because it pulls 2x thread. So that is the important thing to understand here. Okay, so that means the ratio of displacements of A and B is like this. So the ratio of accelerations of A and B will also be like this. Acceleration of B will be twice of acceleration of A. So this is the constraint relation here. This is the constraint. Okay. So now from the constraint relation, we'll understand that if this has a horizontal acceleration of small a, then this will have a vertical acceleration of 2 times small a because of this from equation 1. Okay, and the rest is of course very simple, free body diagrams. So for this blocks FPD, there is only 2 forces. For this, you don't need to worry about the weight, that is balanced by the normal reaction. So for the block A, you can see that horizontally there's a force of 2 tensions, 2T acting like this. Okay, and its mass is 2m and its acceleration is A. So we'll have the equation 2T is equal to its mass 2m into A. So that's our second equation. And for the block B, of course, it's very simple. We just have tension and weight and downward acceleration of 2a. So mg minus t is mass multiplied by its acceleration, which is 2a. So that's our third equation. So now just solve equation 1, 2 and 3. Okay, so 1 is already taken care of because we have taken this. Okay, so we have 2t is equal to 2ma, that is equation 2. So from this we can take t is equal to ma and substitute this in equation 3, which is mg minus t is 2ma. So mg minus ma is 2ma. So this will give us mg is equal to 3ma, or a is equal to g by 3. So a is equal to g by 3 further means that the block A will have an acceleration of g by 3 horizontally like this, whereas the block B will have an acceleration of 2g by 3 because it will be 2a and downwards. So these are the accelerations. So make a note of this first, then we will look at the second part of the question where you have to find the reaction force at the clamp again. So we'll discuss about that also. Okay, now let's come to the last part of this question. So in 31 again, the last part, you have to find the force exerted by the clamp on the pulley A. So for that, you have to first find the tension. Okay, so you can see that from this value of A, you already know the value of tension. So we know acceleration. So from this, we also know that the tension in the string, which is MA, is mg by 3. So now the C part you have to find the force exerted by the clamp on pulley A. Force exerted by the clamp on the pulley which they have labeled as A. So going back to the diagram, this pulley is labeled as A and this pulley is labeled as B. So on this pulley, you have to find out how much force is exerted by the clamp. And again, the pulley is massless. So it's a massless pulley. So if you look in this diagram, what all forces are acting on the pulley, there is a horizontal tension acting towards the left. There's a vertically downward tension acting. Okay, and there is the reaction force at the clamp. So the net of those three forces has to be 0. So make the free body diagram of the pulley. So there is tension T acting like this. There's one tension acting vertically downwards. So these two tensions together are pulling it like this. Their net will be along this direction. So the reaction force will be opposing that. It will be acting like this. So let's say this is the reaction force, okay, exerted by the clamp on the pulley. So the vector sum of T and T, which is at 90 degrees, has to be balanced by this reaction force. So you can see that the reaction force will be T root 2 in magnitude, and it will be at an angle of 45 degrees. So it will be, now you can see T was this much. So mg root 2 by 3 at 45 degrees with respect to the horizontal or vertical, whatever you write that. That will be the reaction force at the hinge. So that is attached to the clamp ना. It does not affect the pulley. देखो क्या हो रहा है, वो pulley ऐसा है. Now this part of the string, it's attached to the clamp. It's not exerting any force on the pulley. It's like this. So this tension is acting here. It's not acting on the pulley. Is the point clear, Aman? Yeah. So that's important to understand. Right? Okay. Fine. So that's done. Let's come to question 33 now. 33 is an important question. So 33 is related to an example question we've done in class before, which has to do with the concept of pseudo force. But it's not exactly the same. I just said it's related to that question, but should be able to recall. So in 33, what is happening is that we have this kind of situation where we have this triangular wedge on this surface, on this smooth surface, and we are pulling it towards the right through the action of by the tension in the string. Now the tension in the string is produced in the first place because on the other side the string is attached to a block which is hanging vertically like this. So this angle is theta. This is a smooth surface. Now this wedge has a mass m prime. This block has a mass m. And on top of this we have kept a smaller block which is of mass small m. And this surface is also smooth. So we have to find m such that the small block, this one small m, does not slip with respect to the inclined surface of the wedge m prime. Okay, so that means that this system is pulling it with an acceleration e. Now that acceleration is enough that with respect to that smooth surface, the small block m will not be sliding down. Okay, so recall that we had done one question like this, where that question we were doing this, that if we push this with enough force, it would generate enough acceleration for this so that the pseudo force acting on this would prevent it from sliding down. So that same thing is happening over here. The acceleration towards the right will generate a pseudo force towards the left on the smaller block. And if that pseudo force is enough, it will balance it from sliding down the inclined plane. So what we have to understand here is this main thing, that small m is not slipping with respect to the inclined surface. So what this means is that for the FBD of the block small m in the non-inertial frame, of the wedge m prime, what should happen? Forces should balance, or it should be in equilibrium. That is the condition you have to apply. Okay. So just recall this question and you'll know what to do. Make the free body diagram of the smaller block in the non-inertial frame of the wedge and apply the condition for what? The condition for equilibrium. So the condition for equilibrium will give you the value of A, and once you get the value of A, from that you can now solve for the value of this block, capital M's mass. Okay. So just try out the steps I've told you over here, because this is an important type of question. You should know how to solve this. Okay. Just start with the free body diagram. I'll verify it for you in a moment. Okay, so anybody got the value of A from the free body diagram? So let's discuss. See what is happening if you are in the non-inertial frame of the wedge. Okay, so basically you are standing on the wedge, and with respect to you, what is happening? This block is not moving; it's at rest. Okay, but remember, you yourself are moving with an acceleration like this. Okay, so when you make the free body diagram of the wedge in your frame, that is the frame of the wedge, which is a non-inertial frame. So because that frame is moving with an acceleration E, the block will first of all experience a pseudo force, which will be small m into A, because its own mass is small m. So its mass into the acceleration of the frame. So this is your pseudo force. Okay. And then apart from this, of course, there will be the weight of the block, mg, which is acting vertically downwards, and normal reaction, which will act perpendicular to this inclined surface. So this angle is theta. You can see here this angle is theta, or this angle is theta. Now in this frame, this wedge should be at, I mean, this smaller block should be at rest. So the forces should be balanced. So now what you do is you take the components of the force. So pseudo force will have one component like this, ma cos theta, and one component like this, ma sin theta. Okay, so pseudo force is taken components of. Mg will have one component like this, mg cos theta, and one component like this. Let's write that in a different way. Okay. Yeah, so mg's components be like this, mg cos theta and mg sin theta along the inclined plane. So mg's components we have taken. Okay, and normal reaction will of course act. So this, and they should be balanced. The acceleration of the block should be 0. Okay, so forces should be balanced. So along the inclined plane, along this direction, when you balance the forces, what is happening? Mg sine component should balance pseudo forces cos component. So this is our important equation actually. This will tell us that A should be equal to G tan theta. This is the result we are looking for from this free body diagram. But how much is the acceleration that we require? So we require this much. And the other will just tell you the value of normal reaction. It is mg cos theta plus ma sin theta. So that's your second equation. So this we won't really require that much. Okay. Now next what we'll do is, so we have found out the acceleration. Now for this, for A to be g tan theta, we need to find out how much should be the mass of that other thing which was hanging vertically. Okay, so we need to find that out. So for that, what we'll do is now this block plus wedge. So wedge of mass m prime, block of mass small m. This whole system is moving together at a common acceleration of g tan theta. So this should also be going down at the same acceleration of g tan theta. And this, okay. So one make the combined free body diagram for the wedge m prime plus the block small m on it. Okay, so this whole thing combined FBD. So on that combined FBD, there's only one horizontal force, tension. The rest are vertical forces. And this system is having a horizontal acceleration E. So tension should be equal to m prime plus me, that is m prime plus m g tan theta, because this A should be equal to g tan theta. And then for this one's free body diagram, this block, we have weight minus tension is equal to ma. So we have m into g minus a should be equal to t. Okay. So substitute this here. So this is our equation 1, this is our equation 2. So substitute this here. So capital M into g minus g tan theta should be equal to t, which is m prime plus m g tan theta. So from this you will see, you will get m as m prime plus m tan theta upon 1 minus tan theta. So you got the unknown value. Okay, so this is the complete solution of this question. So this is one of the more difficult level questions for this chapter. So first of all, make sure you understand this thing, that the free body diagram of the small block, okay, in the wedges frame, that is in the non-inertial frame of the wedge M prime, and from that how we are getting the value of g tan theta, acceleration as g tan theta. And the next stage what we do is we substitute that in the next set of FBDs to find out capital M. Okay. Also the answer is given in the form of cot theta. So for that we'll just have to replace tan theta with 1 by cot theta. I'll explain how that's happening also, but that's very easy. Okay, so now you substitute that value of A in the combined free body diagram. Okay, for the block plus wedge, and of course the free body diagram of the other vertically hanging wedge. Okay, so it's weight capital Mg acting like this, it having a downward acceleration. Now in the final answer, what you do is you replace tan theta with 1 by cot theta. So that way you will get the answer the way it's given in the answer key at the back. This will become 1 by cot theta upon cot theta minus 1 upon cot theta. So it just becomes this. Okay. So this is equally correct, but just that the answer is given instead of in terms of tan theta, it is given in terms of cot theta. Okay, so this was one of the important questions in this chapter. Now let's move on to 39th after this. Oh, sorry, 37th. Okay, so let's first go through 37th question. So 37th question is the one where you have that monkey climbing the rope that goes over a smooth light pulley, and on the other side there's a block of the same mass as the monkey. So you have to show that both of them will move in the same direction with the same acceleration. Okay. So what is happening is you have a block of mass m on this side, and on the other side you have the monkey of mass m. Now suppose the monkey starts climbing such that it has an upward acceleration of a. So what is happening is that means the tension in the string which is acting on the monkey is larger than its weight, no? Because it has an upward acceleration. So if this has an upward acceleration a, it means that T minus mg is equal to ma. So the tension in the string is m times g plus a. And this tension is the force with which the monkey pulls the thread or the rope down. So that becomes equal and opposite to the force with which the rope pulls it up. So the monkey is pulling down with a force F. So that force only is equal to the tension T. So this is equal and opposite upward force of T is applied by the rope on the monkey. Okay. So that thing. So now you come to the FBD of the block on the other side. That's also experiencing the same tension and the same magnitude of weight. So it will also have the same acceleration. If its acceleration is a prime, T minus mg is equal to ma prime. Now you compare this equation with the first equation. So comparing the two, you can see because the masses are the same of the block and the monkey, a prime is equal to a. Okay, so whatever upward acceleration the block is having, the same, I mean, whatever upward acceleration the monkey is happening, the block will have the same amount of acceleration upwards. So that means the relative acceleration between the block and the monkey will be 0. That will be 0. No, because relative acceleration is the difference of the two. So that is why there won't be any relative displacement. This is the relative acceleration of the block with respect to the monkey. Okay, and that will be 0 because both are the same. You know that acceleration of any object A with respect to another object B is the acceleration of A minus acceleration of B. So here what is happening, the acceleration of the block, that is also plus a j cap, is going upwards. The acceleration of the monkey, that's also plus a j cap. So their difference is how much? It's 0. So there is no relative motion. So that is the final thing in the question. So make a note of this and come to question 39 after this. If you've already done this question, then come to 39, and in 39 start with making the free body diagrams of two separate things. One is the elevator box and the other is the person standing inside it. Make two separate FBDs, one FBD for the person and one FBD for just the box of the elevator. So that will give you a very easy way to solve the question. Okay, so hope question 37 is clear. Now let's come to question 39. So in 39 you have this situation. You have like an elevator box. Okay, and inside the elevator box there is like a weighing machine on which this person is standing. And while he's standing, he's also pulling down on a thread or more like a rope. So that rope is going through a gap in the box. Around a pulley like this, and the other side of the rope is fixed to the box. It's fixed at this point. Okay, so now the person inside, he has a mass of how much is it, 60 kgs, and the elevator box is having a mass of 30 kg. Okay, so we have to first of all show the weight reading, okay, of the weighing machine when the box is at rest. The person is pulling such that the box is at rest. So at that point of time, this weighing machine, what kind of reading it is showing? So remember, the reading of the weighing machine is the normal contact force. If the normal reaction is N, the normal contact force, then the reading shown by the weighing machine will be the normal reaction divided by G in kgs. Normal reaction is in newtons, so it shows that as a reading in kgs, so that divided by G. Okay, so for that condition, if he is pulling down the rope with a force F, the rope will have a tension T. So that tension is equal to the pulling force. So for the first part, when you make the person's FPD and you make the box's FPD, so what is happening? The person is being pulled up with a tension T. Gravity is pulling down with a weight of 60 G, and there is some normal reaction acting on his feet upwards like this, and the person is at rest in ground frame. This is in inertial frame. Okay. Whereas if you look at the box, it's experiencing one tension upwards where the rope is attached. Normal reaction that the person is applying and its own weight, which is 60 G, which is 30 G. Okay, and the box is also at rest in the ground plane. So you have one equation that T plus N is equal to 60 G from the person's FBD, and you have the other equation that T is equal to N plus 30 G. So that's your second equation. So just add the two equations, you will get 2T is equal to 90 G or T is equal to 45 G, and substitute that and you will get N is equal to 45 minus 30 or 15 G. So that means the reading, the weighing machine will read how much? 15 kg. It will show a reading of 15 kg because the normal contact force is 15 Gs. Okay. So just make a note of this part first, then we'll come to the second part. In the second part, he's pulling with a greater force so that the system has an upward acceleration. So we have to modify the equations a little bit, though the free body diagram will remain the same. The second part is now asking that how much force should he exert downward so that the weighing machine shows his true weight. How much force should the person apply on the rope so that the weighing machine shows the correct reading? Okay, so the weighing machine is reading the true value of his weight. That means the normal reaction should be equal to 60 G. So for this, how much should be the force that he's applying? Remember, the force is equal to the tension in the thread. So just make a note of the first part if you haven't done this question, and otherwise start working on the second part. Okay, very good, Aman. So let's verify the second part. So what is happening is that if the force he applies is more than this 15, sorry, this value of tension which was 45 G, if he applies a force greater than 45 G, okay, because in part 1 F was equal to T was equal to 45 G, that was giving zero acceleration to the system, but the normal was 15 G. So if he applies a force greater than this, what will happen? Acceleration will become non-zero. Both the box and the person, they will now have an upward acceleration of A, and the normal force will become greater than 15 G. So coming back to the free body diagram, on him, again both of the FBDs we are seeing in the inertial ground frame. So on him there is this T, his weight 60 G, and some normal reaction such that there's an upward acceleration of A. So this time N plus T minus 60 G is equal to 60 A upwards. That's our first equation. And similarly on the elevator's box, okay, again the forces are the same. Tension, normal reaction acting downwards, the weight of the box 40 G acting downwards, but the box is also going up with the same acceleration A, because he and the box together are moving with an acceleration A upwards. So we have the equation T minus N minus 40 G is equal to, oh sorry, not 40, this is 30. My mistake. Mass of the box was 30 kg. Yeah, so alright, so this is equal to how much now? 30 A. So this is our second equation. Now we want to find the value of T so that N should be equal to the true weight of the man. So we want N should be equal to how much? 60 G. So substitute that over here. So 60 G plus T minus 60 G should be equal to 60 A. That becomes our first equation. So T is equal to 60 A. Okay, and substitute that here. So we get T minus 60 G minus 30 G is equal to 30 A. So T minus 90 G is equal to 30 A. So that becomes this equation. Now substitute this here. So we can substitute 30 A as how much? T by 2. Okay. So T minus T by 2 should be 90 G. So that means T by 2 should be 90 G, or T should be 180 G. So that means the force he should apply, which is equal to the tension, should be 180 G. Or if you take G as 10, it should be 1800 newtons. Taking G as 10 meters per second square. Okay. So this is the complete solution of the second part. Okay, now 41 and 42, I will just quickly give you a hint on how to solve these questions because they are based on the very simple concept of pseudo force. Okay. So in question 41, what is happening is that you have a car moving with a horizontal acceleration A. Okay. And inside this, in the first case, you have a bob which is suspended. So if that bob is suspended in equilibrium, it will be at a position like this. Why? Because there will be pseudo force acting on it. If that particle has mass m, there will be pseudo force acting on it, there will be mg acting on it, and there will be the tension in the string acting on it. So it is just about equilibrium of the three forces. Just use that equilibrium of the three forces condition and you will get the angle theta at which the string is going to be inclined with respect to the vertical. So just balance these forces. T cos theta balances mg, T sin theta balances the pseudo force. So you will get tan theta equal to E by G. Okay. Now similarly in the second part, you have to find the condition that on the inclined plane, on a smooth inclined plane, an object is kept and it does not slip. So what is happening? The same car moving with an acceleration like this. How come an object kept on an inclined plane will not slip? Because of pseudo force. So that means the inclined plane must be like this. If it was the other way, then it would definitely slip. And the object kept here, the pseudo force on it will be acting in such a way that it does not allow it to slip. So this is just like that question we were doing earlier today. So if this is not slipping, then in this frame it should be at rest. So you'll see that you'll get the condition that pseudo force's cos component will balance mg sin component. So again in this you will get E equal to G tan theta. But in this case theta is the angle of inclination. This one. Okay. And 42nd question, what is happening is that you have an elevator with a box kept on the floor. Now this starts accelerating at something which is more than g, 12 meters per second square. So what will happen is as it starts accelerating, the elevator is accelerating at 12, but immediately the box loses contact with it because the pseudo force becomes more than the weight. This is going down only at g. So that's why it starts. So if you're looking at it from inside the elevator in the non-inertial frame, you will see that on the box there is an upward pseudo force and there's a downward mg, and you'll see this is more than this. So the box will have, with respect to it, will have an upward acceleration of ma minus mg divided by mass. So that will make the box actually go up in your frame. There's actually in ground frame what is happening, the elevator is going down faster, the box is going down slower. So the box is also going down, but the elevator is going down much faster in comparison. So inside this it looks like it's going up. So both these questions are just about application of pseudo force, so I don't think you should have any difficulty. Now we'll discuss about spring force. It will hardly take few minutes because it's a very easy concept. But as I said, for your upcoming major test 4, make sure that you are prepared with all the questions of H.C. Verma and the concepts used in that. That is the concepts of pseudo force in non-inertial frame, pulley systems, constraint relation in multiple pulley systems, okay, and all sorts of normal contact forces and reaction force at hinge of a pulley and these kind of things. So all those concepts are covered within the HC Verma exercise. And once you are done with all the doubts and cleared all the questions of HC Verma, for additional practice, you have to complete the module exercises also. And we will keep some time for discussion of the module exercises also. However, the module exercises have mixed questions in friction as well as Newton's laws. So we will be discussing those questions together after we cover friction. So you have still got some time before you can finish off your module exercises, but please make sure that you try and finish maximum questions from HC Verma before your next major test so that you're able to attempt all the questions in major testing. If you're able to solve HC Verma questions, you have nothing to worry about in Newton's laws of motion. You are ready to move on to the next chapter, which is friction. Okay. All right. Now let's talk about the last thing in this, the spring force. So this is something very simple. A spring is a device which works on the principle of elasticity. So a spring is a device like this. Spring is made by it is made by coiling of a thin metallic wire. Okay. So you basically take a thin metallic wire like this and then you coil it into this. So the shape you get is called a spring. And this shape has the property, so a spring has a property called elasticity, just like a rubber band actually, but it works both ways in the case of spring, both for compression and expansion. It means that in order to extend a spring, so if this is the natural shape of a spring, we'll denote its length as L. So L is what we call the natural length. That is, when we are not subjecting the spring to any force, then it has its natural length. So when we want to stretch it from its natural length to a larger length, in order to stretch it, we have to apply an external force outwards like this on both the sides. And as a result of that, the spring gets stretched to L plus X. But the moment we stretch the spring, it applies an inward tensional force like this. Okay, so that inward tensional force has a tendency to make it come back to its natural shape. So that tendency is only called elasticity. Okay, so when stretched, okay, to a length L plus X, okay, the spring develops a tension, or it is also called restorative force. It tries to restore it back to the natural shape. So that tension is actually directly proportional to X. In fact, that tension is equal to Kx, where the quantity K is called the spring constant. Okay, the spring constant is expressed in newtons per meter. So this is a property of the spring. Any spring has a particular value of spring constant, and that spring constant depends on a lot of things, including what metal the spring is made of, the length of the spring, the density of the coiling, the shape of the coiling exactly. So it depends on number of factors, the material of the spring as well as the geometry of the spring. All these factors it depends on. Okay. So the spring constant is not something that we can derive by a formula, rather it is something that is experimentally measured. But as it turns out, the more we stretch the spring, the more will be the tension force. It will be directly proportional to X. So that is the important elastic property of the spring, that when you stretch it, the internal tension it develops is directly proportional to how much you are stretching it. So this is the important formula for a spring. It's called the spring force formula. The spring force is equal to the spring constant multiplied by the extension of the spring, in the case where we are extending it. Okay. So for example, if we have vertically suspended a block using a spring and it's in equilibrium, so a block of mass, let's say 10 kg, is vertically suspended using a spring of spring constant, let us say 25 Newton per centimeter. Okay. Now, one more thing you should understand, that an ideal spring is massless. That is, its mass is negligible. Okay, an ideal spring. So, in all these questions where a spring is given to you, you'll always assume that it's an ideal spring and it is massless. that is of negligible mass. So the spring might have a mass of few milligrams or something that's negligible compared to the mass of the block. So now we want to find the extension x in the length of the spring due to the weight of the block. So this is a very easy situation. You can see here that because the spring is in an extended state, it will be applying this kind of inward tension over here. So when you make the blocks free body diagram, and that tension will be equal to how much? It will be equal to kx. Yes, Prince, if you have some question, you can please ask me. So when you make the blocks free body diagram, the upward tension acting on it through the spring, that is equal to kx in magnitude, and that has to balance the weight. That has to balance the weight of the block because the block is in equilibrium. It can, if the force is providing acceleration, then it will be equal to ma. But here there are two forces. Yes, k would be given in the question always. Okay, k would be given in the question, or you can, it can be a reverse question that x is given to you and you are asked to find the value of k. But whatever, you have to always use this expression. So here the acceleration of the block is 0. That means the tension is balancing the weight. So the tension here is how much? It is kx, and that is equal to mg. So the amount of extension in the spring is nothing but the weight of the block divided by the spring constant. So the weight of the block taking g as 10, you can see is 100 newtons divided by 25 newton per centimeter. So we don't need to convert the unit, and we can see x will be just 4 centimeters. So the spring is extended by 4 centimeters because of the weight of the block. Yes, for the same spring that you are using, k will be same everywhere. But if you are using a different spring, it will have a different value of k. This might be a copper spring. I might replace it with a silver spring or with a aluminium spring of the same geometry, but material is different. So k will be different for you. So different springs will comparatively, yes, we are coming to that also. We are coming to the compression also. So this is an example of the extension of a spring. Now, just like the spring has the property of developing tension equal to kx on extending it, the same thing happens when the spring is compressed also. So if this is the natural length of the spring, then we can always compress the spring by applying inward force on it. So this time the external force has to act inward, but the spring develops an outward tension. So again, it's a restorative tension. It tries to restore the spring back to its natural shape. Okay, so if the spring is compressed by x, so its length compresses to L minus x. So in a compressed state, okay, length of the spring is becoming the natural length minus x. Again, the spring develops an outward instead of this time inward tension or restorative force. And again, this tension is equal to kx in magnitude, where k is the spring constant. So whether a spring is compressed or it is extended, it will exist like this. Okay. So for example, we have a situation like this that we have attached a spring like this to a wall, and the spring is of constant, let's say 20 Newton per centimeter. Now we are pushing it with some force like this at this end, and we want to find the compression X, if the force we are applying is, let's say, 50 newtons. So we can see over here that the force we apply externally like that will result in compression and an external tension acting like this. That tension will also act on the wall on the other side. So the wall will have to apply a reaction force. This will be reaction force at the wall. Okay. And ultimately F will be equal to T will be equal to that reaction force because the spring is at rest. So F will be equal to Kx because the tension is always equal to Kx. So again X over here will be F by K. So it will be 50 newtons divided by 20 Newton per centimeter. So Newton cancels, per centimeter comes on top, and the value of X is 2.5 or 5 by 2 centimeters. So if you're pushing this particular spring, which has K of 20 Newton per centimeter, with a force of 50 newtons, yeah, the spring constant is the same. I mean, a particular spring will have this a particular value of K. So whether we compress it or extend it, the tension developed will have a magnitude of Kx. If you compare two different springs, of course, they will have different values of K. But the same spring, whether we compress it by 1 centimeter or we extend it by 1 centimeter, the tension developed will be K into 1 centimeter. The difference will be in the direction of tension. When we compress it, the tension is outwards because it's trying to restore it back by stretching itself back to natural length. When we extend it, the tension is inwards because it's trying to restore it by pulling it back to its natural length. No, and it is not that way. We are applying the force to compress the spring. Now the spring applies its own outward force because it is elastic in nature. It's the property of elasticity of the spring. Like if you take a solid block of rubber and you press it, what will happen? It applies an outward force on your hand. No? It develops an outward tension. Whereas when you take a rubber band and stretch it, the tension acts inwards. So that is the property of elasticity. Like rubber has elasticity, like that a spring also has a property of elasticity. Okay, so that completes the Newton's laws portion. We'll be starting with friction in the next lecture, as I told you. Okay. However, at the time when we are discussing questions of friction, we will also be discussing questions from the module exercise for friction. Sorry, for Newton's laws of motion, because the module exercise has both friction and laws of motion questions together. Okay, combined. So we'll be discussing the module questions while discussing friction. But please complete HC Verma, if possible, each and every question, because that will ensure that your concepts are 100% clear in Newton's laws of motion. Okay, so that's it. That's it for today's session. People, wish you all the best.